6.7, Stokes' theorem. In short, Stokes' theorem is one way to generalize Green's theorem. Remember, there are two forms of Green's theorem. We can look right here at the statement of Stokes' theorem, that it's an equation relating one integral with another integral. On the left, we have a line integral, and then on the right, we have a surface integral. The line integral should look familiar in that we're taking a vector field and we want to go with the curve. So this would be circulation. And the restriction is that we need for the curve to be simple. It doesn't cross itself, and then it's closed. Where it begins, it also ends. And then by doing that, we want that curve to be the boundary of a nice, smooth surface S. So we're getting that the circulation about the boundary of a surface can be related to a surface integral over the entire surface, where we take as integrand the curl of that vector field. Okay, very nice. So here's a picture. And in this picture, it's worth noting that the difference between Stokes and Green's is that the surface can occupy 3 space, or can sit inside of 3 space, whereas Green's, the surface must be a region in the plane. It must be flat. Nice. And then here they make the observation how Green's and Stokes are related. When we have a vector field in the plane, we typically write P and then Q, so that if we wanted to find a line integral over a closed curve C of this vector field, we can write that out as a closed line integral P dx plus Q dy. And then by Green's, if the curve C is closed, it would enclose a region D. And then we would look at the second component and partial it with respect to the variable of the first component, namely Q sub x, and then take the first and partial it with respect to the variable coming second, P sub y. That would be the integrand, and as this is a double over a flat region D, we get dA, and then I like to just write xy, default x's and y's. So that's Green's. And then we saw that Stokes is the same thing, but that curve C can be the boundary of any surface. And then what you would want to recognize is that this is curl of the vector field, which really doesn't make sense when the vector field is only a 2-vec, but if you throw in a third component as just 0, then you can take the curl of that and you would find that the kth component, so that guy dotted in the k direction, would exactly equal this. And that's what ends up happening in the full-blown Stokes version. All right, so in this case, that F vector field is not this one, since you would need a third component, R. This is just showing how Green's and Stokes are related. All right, so in the book, you can look up a specialized proof of Stokes. I'm not going to go over that. I'm going to go over this example that they have where they verify. So you have a theorem, and the theorem is saying that one quantity equals another quantity. And so we're going to look at one side and then look at the other side and then check that indeed they are equal. All right, so what are we working with? Well, we have a vector field, y to z and then x squared. That's the vector field. And then we have a surface, this paraboloid, and they give it to us. Z equals 4 minus x squared minus y squared. They tell us that it should be outward oriented and that this surface is good for z's bigger than or equal to 0. So if it says outward, that would be positive, so positive direction rather than inwards, the negative direction. And then when you want to do that, what you can do is you can take this equation and you can bring everything to one side, and then bring everything to one side so that the isolated guy stays positive. So that would be subtracting this to the other side. So 0 equals z minus 4 plus x squared plus y squared. Then call that capital F of x, y, and then compute grad f to find that you get partial of capital F with respect to x gives you 2x, and then 2y, and then positive 1. So this is the normal direction. This is not a unit vector. This is only the normal direction, not the unit normal. And that is for our surface being outwardly oriented. Okay, so we'll need that and that. All right, so let's take this vector field and compute its curl. So there's the vector field, and then compute out its curl. All right, you can verify that. We want to verify Stokes. We're going to look at a double integral, and we're going to find we get negative 4 pi. And then we'll look at a line integral and verify that we get the same quantity. On the surface integral, we have as integrand curl of the vector field. Here it is. You've verified that, and so there it is. It pops up. And then on the surface area differential, written out in vector form, we know that we're going to get the normal direction, which is the tangent cross the tangent, or as we computed up above, grad capital F, and let's go recall what we found. 2x, 2y, and 1, and again that was so that we have an outward orientation, 2x, 2y, and then 1. So that's what we have here, 2x, 2y, and then 1. This is the normal direction against a regular area differential in the flat. And in the flat, this is just the projection here, that circle, and then that's going to be a circle in the xy plane. In the xy plane, the z is going to be 0, and therefore you can move the x squared, y squared to the other side. X squared plus y squared equals 4, and then that's why they're coming up with this description of D. Excellent. Okay, so that was a surface integral. We want to verify that that's equal to the line integral, or evaluation on the boundary. And as we just mentioned, that circle, the boundary, is x squared plus y squared is equal to 4, which means that it's a circle of radius 2. And the orientation is counterclockwise. So we get that the position vector for this curve C, oriented counterclockwise, is 2 cosine t, 2 sine t, and it's occurring in the xy plane, so z is 0. And we want to make a full revolution, so we let t vary from 0 to 2 pi. Our vector field was simply y, and then z, and then twice x squared, x squared. So 2 times 2 gives you 4, and cosine squared is cosine squared. And then you dot that in the tangent direction to the curve, which is just given by the tangent of the position vector. Cosine derivative goes to negative sine, sine goes to cosine, and the derivative of 0 is 0. Excellent. Come up with a nice simplified integral. That's sine squared. You can use a half-angle identity and plug that out and verify that you get the same quantity as we found before. Okay, so Stokes' theorem, evaluation on the interior equal to evaluation on the boundary. And then one last example using the Stokes' theorem. Suppose that we wanted to evaluate some surface integral where the surface is really, really complicated. Well, if the integrand takes a good form, in this case, a surface integral with integrand the curl of a vector field, then we know by Stokes' theorem, provided that we have good domains S and C, that we can push away from the interior and just move to the boundary. And we have to open up the rest of the problem to find out what the boundary actually looks like, and then they tell us that the boundary is just a circle of radius 1. Let's take a look at that. There's the parameterization. Let's go look at the picture. And if you looked carefully, you would have seen that we have changes in x, changes in z's, but no changes in y's. So y is going to be 0, as this is in, c is in the xz plane. And what they're going to do is they're going to start at the origin, and then they're going to move out that way and come around like that, assuming that that is x positive. So they want x's to begin growing from 0 to get positive, then come back to 0, and then x's go negative, and then come back to 0. They're going to want z's to begin at 0 and then grow bigger and bigger and bigger. Here is z equal 1, so that's z equals 2. And then come back down to 0. And then let's just verify that. The position vector that they use has sine t, 0, 1 minus cosine t. So x's begin at 0, sine of 0 is 0, and then sine, think of the sine wave, grows and becomes positive, and then positive, and then comes back to 0, and then goes negative, and then back to 0. So that looks good. With t beginning at 0, when t is 0, cosine of 0 is 1, 1 minus 1 is 0, so that the z's will begin at 0, and then as cosine begins at its largest quantity and then dips down, 1 minus a smaller and smaller quantity will get bigger and bigger and bigger until cosine goes to be negative, and cosine turns negative after pi over 2. And then cosine has its smallest negative value at pi, negative 1, so 1 minus negative 1 is positive 2. And so that looks good. No typos there. Okay, so again, we're asked to evaluate a surface integral, and the integrand is nice. The surface, we assume, satisfies all of Stokes' requirements so that we can push to the boundary. Then pushing to the boundary, we're going to need a parameterization of that boundary, and that's what we have just verified. So that we can take the surface integral we're asked to evaluate, use Stokes to recast it as a boundary integral, and then having a parameterization of that boundary, we can write it out as a simple 3a integral in t after we do a dot product. So right here is the vector field. We have to go back and look at what the vector field is. They give us the vector field z, 2xy, and then the sum of x and y. So when we look at the first component, z, that's 1 minus cosine t, and there it is. The next component of the vector field is 2xy. Since y is 0, 2xy is just going to be 0. And then the third component is the sum of the first and second components of the position vector, so that's just sine t. Looks like they have a typo there with that minus sign. All right, and then the dr vec is just, yeah, they made another typo. This should be the derivative. So sine should go to cosine, and this should go to positive sine. Okay. So Stokes' theorem, very, very useful, and it's a generalization of one of the forms of Green's theorem. Nice.